I guess it's about time we start. So welcome everybody. My name is Julian Tierney. Oh, maybe I will remove the mask if that's okay. I guess the speakers can do that. Probably you can hear me better like this. Welcome to the TTK tutorial at IEEE Viz 2022. It's a pleasure to see you guys after those 2 years of pandemic. So I will just say a few words about the organization of the tutorial, and then I'll hand the microphone to the other presenters. But obviously, TTK is about topological methods for data analysis on data sets that are defined on meshes or things that you can mesh. And everything that the library provides is a sort of Swiss Army knife to analyze your data. And one of the cool things that you have with those methods, as you will see, is that they're robust, they're multi-scale in nature, and they also have a great interpretability. So TTK was started back in late 2014, and we used it internally for our own developments. And by 2017, we released it open source. And ever since, we have the pleasure to have 17 different institutions which contributed code to the repository. And last year we reached a big milestone for the community in the sense that TTK was officially shipped in PowerView 5.10. So this is a major data analysis and visualization application. And for the next releases of PowerView, TTK will also be shipped in. So what is new in TTK since the last tutorial? I will just do a quick refresh for those of you who attended the other tutorials, and you will see what are the new features. One thing that we're pretty happy about is not a feature of the library per se, but it's a new website that contains a database of examples. And if you go to this website, this looks like this. You have some categories of examples, for instance, for high-dimensional data, ensemble data. And for each of them, you have a few examples. Let's take this one. And for each of them, you have a screenshot or a video. You have a complete description of what the pipeline is doing. You have the command line to reproduce the screenshot. And you have a snippet of Python code to exactly reproduce the analysis. And you have links to the documentation. So you'll see you have like 30 complete analysis examples that you can reproduce if you install TTK, and you can have an understanding of what's going on. So we've been working on this actively. This may look simple, but this is some work, and we're happy to have put that together. So let me put the presentation again. Sorry. Right. Another cool thing that we have since the latest release of TTK is a new backend for persistence diagram computation, which is based on this technical report, and which computes persistence diagrams. And this is specialized for data sets defined in 3 dimensions. And actually, we have a benchmark where we compare the performances of this algorithm to 15 other public implementations. And we have many accelerations that make it a little faster. And this is still work in progress, but it's already available in TTK, and you can compute your diagrams quickly with this. There's a byproduct of this algorithm is that you can compute persistent generators in data set, and this is related to another talk that will be presented later this week by Federico. The technique is highly related, although it's a bit different, but Federico will talk much about that later this week. We also have RIPS complexes for high-dimensional data. So if you have high-dimensional data, you can put that into TTK and do some analysis. There's a few caveats, but if you're interested in the low-dimensional features of your data and the high-dimensional data, we can grab that. We also have backend for persistence diagram approximation that have been emerged recently. We also have a new data structure to represent triangulations internally that is called the compact triangulation. And there will also be a talk later this week at Viz about this data structure by Federico's group. And in TTK, it's really easy to activate that, so you can basically reduce the memory footprint of the data structure if you need, and we have a new triangulation manager that enables you to do that. And we have various other things, bug fixes, documentation improvements, and all that. Installing TTK has never been easier. I would recommend simply to go to the PowerView official website. You click on download. You may want to try the release candidate version for 5.11. That way you have the latest TTK features. So it's just a matter of downloading PowerView, enabling the plugin, and you can do everything that we will show this morning based on that. So if you haven't installed PowerView now, I would recommend that you do it because we'll have a few talks that will be introductory. And by the time you downloaded it and you installed it, you'll be able to reproduce exactly what is shown on the screen. And also on the web page of the tutorial, there's a data package that you can download, and that contains all of the data that we'll use this morning. All right. Of course, if you want to install TTK differently, there's plenty of alternatives. And again, we have the website that contains many resources, including video tutorials and things like that. Okay. So when it comes to the tutorial, the talks that we'll do this morning, it's pretty much a sequel of last year with some updated contents and new features. And here's the detailed program. So we'll have a first part that will be an introduction to topological methods by Bay, and then an introduction to PowerView. And then we'll have more advanced topics regarding the internals of TTK, and then we'll have plenty of examples. We were thinking of having 2 breaks, but the coffee will be served at 10:15. So I suggest we have only 1 break at 10:15 such that we can all enjoy some coffee and come back afterwards. I will give a brief reminder. This afternoon in this very same room, we have the Topo in Viz workshop, so topological methods for data analysis and visualization. And also there's a sort of informal get-together dinner organized at this place, Fossler Hall. This is about 30 minutes walk from the hotel. And you are all welcome to join. This is some outdoor restaurant, so that will ease the use of the face mask. And that is pretty much it. So thank you again for coming. And without further ado, I will give the microphone to Bay for the introduction to the topological concepts. Thank you very much.
All right. Can folks hear me? It's good? Okay. I was tasked to give an introduction to some of those topological methods you might see in TTK. And my talk is fairly fundamental, slightly mathematical, but not too much. So let's get started. So as a brief introduction to topological data analysis, also known as TDA, there are a number of tools that has been developed in this field. The field has been active roughly for, I would say, 20 years or so. And what I listed here is just a small subset of the tools, but I consider them to be at the core of TDA. Roughly speaking, there are 2 types of tools. One is centered around what's called persistent homology, and one is centered around topological descriptors. And then both of those is originally rooted in what's called Morse theory. And then at the core of Morse theory, it's what's called critical points of Morse function. And today, I'm mostly going to be focused on sort of description of critical points, persistent diagram, merge trees, RIB graphs, and finally Morse-Mel complexes. And then there's other topological descriptors out there, but I'm going to focus on those examples. And then I'm only going to describe very briefly some of those potential applications. Throughout today's tutorial, you're going to see lots of applications using those core tools. Okay. So let's start with examples, starting with critical points. So at the core of describing about critical points, we need to start talking about Morse function. Let's first have assuming M is a smooth manifold. So if you never have seen the word manifold, it really means that locally, if you're standing on a manifold of k dimension, if you're standing on the manifold, locally it looks like r to the dimension of k, where k is the dimension of the manifold. So, for example, if you're a small tiny ant that is standing on a line, where the line is one-dimensional manifold, that the ant on that line looking at its local neighborhood, it looks like R1. Similarly, if you are ant on the surface, on the two-dimensional surface of a, say, two manifold, then your local sort of neighborhood looks like R2. So that's sort of a very brief description of what I mean by a manifold. And then we first start with a smooth function on the manifold. Then given that, on the left-hand side, this is sort of a function from essentially a one-dimensional manifold to R. On the right-hand side is a function from, say, a two-dimensional manifold to R. And then a point is considered to be critical point if and only if the partial derivative is 0. Otherwise, it's a regular point. So on the left-hand side, what I have marked in red are critical points. They are referred to as local maximum. And then the blue points are referred to as local minimum. On the right-hand side, for the two-dimensional functions, again, the red are local maximum, the blue are local minimum, and then the white are what's called saddle point. When we call it saddle point, is that it looks like the center point of a horse saddle, that there's two directions. If you're sitting on a saddle point, there are two directions. Well, for a regular saddle point, there are two directions where the function is increasing, and then there's two directions where the function are decreasing. If you're standing on a local maximum, the function is decreasing in all directions. If you are local minimum, the function is increasing in all directions. Okay, so those are some of those common critical points for 2D, for 1D and 2D Morse function. Now, if you have a critical point, then the function value at the critical point is called the critical value. And a critical point is called non-degenerate if the Hessian, which is a matrix of a second derivative at the point, is non-singular. So finally, at the core of Morse theory, one of the fundamental concepts is Morse function. So a function is Morse if all its critical points are non-degenerate and they have a distinct function value. For example, the pictures I show here, all those critical points has distinct function value. They are all Morse functions. However, if you have a function that looks like this, where there is sort of a plateau, which means that those the points here are essentially sort of not isolated, and this is a non-Morse function. So throughout today's tutorial, I'm going to work with just Morse function. All right, so that is the concept of a Morse function. Imagine sort of, in general, a Morse function is a well-behaved function because it has sort of non-degenerate critical points / isolated critical points, and the critical points has distinct function value. So they are well-behaved for many reasons. Specifically, in actually implementation, you want to actually, assume this uniqueness of the function values. If your data are not unique, then you apply what's called SOS to kind of perturb the function slightly so that they actually have distinct values. Now, the other mathematical concept prior to persistent homology is a concept of homology. So the idea is if you have a topological space, we use sort of H0 to denote the zero-dimensional homology group. H1 is a one-dimensional homology group, and H2 is a two-dimensional homology group. Of course, those concepts originate from algebraic topology, so I'm not going to the algebraic details. But roughly speaking, the zero-dimensional homology is capturing the generators for the connected components of the underlying space. The one-dimensional homology is capturing tunnels, and then the two-dimensional homology is capturing things like voids. For example, in this case, let's say this is my, this is my sort of like a balloon. And in this particular case, if I'm looking at the rank of its homology group, which means its number of connected components, the rank of its component is equal to 1 because it has one component. The rank of one-dimensional homology is 0 because it does not have any tunnel, but the rank of the two-dimensional homology is 1 because it has a void, okay? So, of course, the classic example when you study homology is and then the rank is also sometimes referred to as Betti number. So this is Betti 0, Betti 1, Betti 2. So in this particular case, if you think about this balloon, it has one component. So the Betti 0 is 1. It has one void, so the Betti 2 is 1. Now, for the torus, which is basically the surface of a donut, the classic example for this is that it has one component, right? Of course, if you take 2 bites right here, if you bite over here, then I break it into 2. But right now, I haven't taken a bite of my donut, so it has one component. The interesting part for the torus is, I want to write 2, is that it has 2 tunnels. What are those? Those are the tunnel that goes around the torus, and then the tunnel that goes around the center. So there's 2 tunnels in this. Another way to think about the torus in the classic example is you take sort of a cylinder and glue both ends together, and that's become your torus. And specifically, when I'm thinking about gluing, before the gluing operation, there is already a specific tunnel that goes around. So this is one of those generators. But when I glue from back to back, it creates an extra generator in dimension 1. So there's another tunnel right here. And of course, because it has a void in the middle, so Betti 2 is equal to 1, which means that there's one void in the center. Okay, so that's about homology. What's next? So once you know homology, I want to introduce sort of persistent homology and persistence diagram. Specifically, I'm going to start with a one-dimensional example. So I have this Morse function right here. This is a graph of the function. And then I introduce something called sublevel set. So my manifold is M. So MT is sort of all the part of the manifold whose function value is below T. Okay? So of course, in this specific one-dimensional example, if I pick a specific threshold right here, then the piece of the manifold that is below this is in the domain. So in this particular case, I have F M to R, where M is a subset of R. So in this case, I'm looking at essentially the part of the real line whose corresponding function value is below a certain threshold. So if I choose a particular threshold right here, then the piece of the manifold that is under this value corresponding to those blue area, okay? And when we study persistent homology, one of the important part is what happened when we pass through critical points as I increase my threshold. And that is also at the core of the Morse theory. So in this specific case, I am going to study a sequence of regular values such that between any 2 regular values, there is one critical value. Okay, I will make that precise soon. But in this specific example, let me erase this. But in this specific example, what we have here is that I am picking up A0, A1, A2, up to A7, where those are regular value, and between any two regular value, there is a critical value. So another way to think about it, between any two function value, there's a single critical point. Then when we actually construct a persistent diagram in the most classic sense, is we're working with what's called sublevel set filtration. So sublevel set filtration is a sequence of sublevel set connected by inclusion. So what we mean by that is that, for example, in here, I pick up a specific function value at A2, and I'm looking at what is sort of in the sublevel set at what is my M A2, which is all the part of my domain that is below my threshold. In this specific case, the part of domain that is below this threshold is those purple intervals. Now, if I actually increase my function value from A2 to A3, correspondingly, I have this sort of orange intervals. And what's important is as I'm increasing my threshold, there is a natural inclusion between my sublevel set. Okay, so which means that the purple pieces are included into the orange piece. This is really at the core of sublevel set filtration, and that leads to study the homology of those sublevel sets. So persistent homology is essentially if you have a sequence of sublevel set that is connected by inclusion, what you do is you apply what's called a homology functor. Essentially, you are looking at the homology of each of those sublevel set and how they are mapped into each other. That's precisely how a persistence diagram is constructed. So formally, the persistent homology studies the topological changes of sublevel sets by applying k-dimensional homology. I give examples where the k is equal to 0, then you are studying how the connected components are related to each other. When k is equal to 1, you are studying how the tunnels are related to each other across sublevel sets, and k equal to 2, you are looking at how voids are mapped into each other. Right? But of course, for my simple example, I'm going to stay with H0, which means I'm looking at how the connected components are mapped into each other. Okay. So for example, in this case, the connected components at M2, there's 2 connected components, and then at A3, there are 3 connected components. And 2 of those purple ones a purple component map to the corresponding orange component. All right, so let's do this together. Giving this one-dimensional function, I'm going to construct sort of the persistent diagram by following the sublevel set filtration. So in this particular case, I am going to say, this is a graph of my one-dimensional function, and I'm going to denote all those critical points from P1 to P6. There are 3 local maximum and 4 local minimum. Okay. So how do we do this is as we actually start, again, we are going to do this in increasing function value. So what's happening is at beginning, if I choose a function value that's below 0, then there's no connected components below this threshold. So my sublevel set is empty. But when I come through the first function value here, then I have a connected component that is born, meaning that there is a piece of, right now what I'm drawing here is instead of drawing the connected component in the domain of the function, I'm actually drawing it in the graph of the function, which they are equivalent, but it's easier to understand. So in this particular case, I'm drawing the piece of the function that is below this threshold, which corresponding to an interval in the domain. So in this particular case, when I pass through P0, there is a component that appears in my filtration. And if I go through the next level right here, then this component actually grows, and then there's a new component that appears. Okay? So what we can say is in the persistent diagram scenario, I have a component that is born at 0, and there is a component that is born at threshold 1, okay? So the 0 corresponding to, the component that born at 0 corresponding to the left piece, the component that born at 1 corresponding to the right piece. As I move forward, at this threshold, just above 2, there's a third component. There's a third component that's born right here. So this is corresponding to a component that's born at 2. And what's happened is that, of course, as I pass through the threshold at that 3, I have the first component. Let me actually use a different color. This blue component keep growing. The green component keep growing. The red component keep growing. And I have a new component, which is a purple component right here. So everything up until this threshold is that I have new component that appear in my sublevel set. And then the most important thing happened when I pass through the last threshold as threshold 4, because right after this, one interesting thing happened is that the green component and the purple component merge with one another. And then this is one of those interesting events that happen when you're constructing the persistent diagram, is when components actually merge with one another. And then our rule is the one that is born later got killed or disappear. In this specific case, when this green component merge with the purple component is, we call the purple component has died, while the green component keep living. So this corresponding to the first finite point in my persistent diagram, which corresponding to a component, this purple component that is born at time 3, and it disappeared at time 4. So this corresponding to a point in my persistent diagram, which corresponding to a component that appear at time 3 and disappear at time 4 because it merges with the green component. Let's do one more, is that if I go through the next threshold right here is just past the level, the threshold at 5. What happened in this case, remember the green component has already merged at this threshold. As I keep going, this component keep growing. And at this particular case, now the green component is going to merge with the red component. But because the green component is born later, so the green component actually disappear. So it has a corresponding, it was born at time 2 and is disappear at time 5. Okay, so that corresponds to a second point in my persistent diagram. So, and so on and so forth. What's happened is that, in this specific case, in zero-dimensional persistent homology, as I'm changing the threshold, I'm looking at how the connected components in my sublevel set appear and disappear. And they correspond to a specific pairing at those specific event point. So in this specific case, what we have is on the left-hand side, I have this one-dimensional function. On the right-hand side is zero-dimensional persistent diagram. And remember I said there is a pair between 3 and 4, which corresponded to a component that is born at time 3 and disappear at time 4, and that corresponding to a point, this black point in my persistent diagram. And I also have a point that is born at time 2 and component born at time 2 and disappear in time 5, and that corresponding to this purple point right here, and so on and so forth. So each of this point in the persistent diagram corresponding to the birth time of the component and the death time of the component. Okay, and of course there is one component, this is actually correspond to infinity, which is there's a component that is born but never disappear in the sublevel set filtration. That's corresponding to the blue component. Because this is a component that is the oldest, so as I increase the threshold to say, beyond 6, there is always this single component that exists as my threshold increase to infinity. So that corresponding to a point in the infinity, which is the component that's born at 0 but never disappear. Okay. So this is just a quick introduction to zero-dimensional persistent homology. Of course, there's one-dimensional and higher-dimensional persistent homology as well. Okay, so persistent diagram, as computed this way, can be vectorized and then can be used as input to sort of machine learning algorithms for tasks like classification and so on. Okay, so equivalent notation, other than persistent diagram, is called barcode. And they actually encode very the same information, except their visualization is different. So remember, I have a component that is in orange that is born at 0 but never disappear. That corresponding to a line segment that is starting at 0 and sort of doesn't, just goes to infinity. If I have a component that is born at time 1 and disappeared at time 5, then I have sort of visualization-wise, I have a bar, which is part of the barcode, that start at 1 and end at 5. Similarly, remember, I have a component that is born at 3 and disappear in 4, then I have a line segment or a bar that start at 3 and end at 4. So the barcode has a lot more algebraic formulations than the persistent diagram. So people who works in applied topology, prefer barcode representation slightly more. But the reason I'm also showing this barcode because this is related to the next concept I want to introduce, which is merge tree. If you have a function, the merge tree records the connectivity of the sublevel set. So essentially, 2 points are considered equivalent if they have the same function value and they belong to the same connected components of the sublevel set for some function value. So the left-hand side is sort of my function, and the right-hand side is the merge tree of this function. So again, what we have is we have all the points that is in blue are local maximum. Those are a local minimum, and red a local maximum. And in the merge tree, I didn't want to do this. The merge tree, the leaves are the local minimum. And then I'm using sort of, in this case, I'm capturing the sort of the connectivity between the sublevel set. So again, what you have is as you are increasing the threshold, you're looking at how the sort of the level set of the function are merged into one another, and that gives you what's called a merge tree. So mathematically, the merge tree is taking the manifold itself and identify 2 points if they are considered equivalent, and it's really looking at the evolution of the connected components as the threshold increase. And the important component is that the merge tree, if you actually decompose the merge tree in what's called a branch decomposition, it actually corresponds to the barcode you just saw. So here is an example in 2D where I have a two-dimensional function. This is, again, of course, generated by TTK. This is sort of the graph of this function. So what we're showing here is sort of the merge tree drawn abstractly, or the merge tree kind of embedded in the graph of the function. So the idea is, as I'm increasing my threshold, I'm looking at the relationship between the level set of the function. In this case, there is local minimum. As I'm passing through this threshold, there's 3 local minimum, which corresponded to the birth of 3 component, which corresponded to the 3 leaves in my merge tree. As I'm increasing my threshold, for example, to right above the white saddle point, then the components that is below here are merged into one another at the saddle point. They're corresponding to sort of the intermediate points, branching points in the merge tree. So as I'm increasing my threshold, I'm really looking at the relationship between different level set of the function and how are they connected with one another. Okay, so that is sort of thinking about the merge tree as a topological skeleton of the sublevel set of my function. And finally, there is what's called a RIB graph, where the RIB graph is considering 2 points to be equivalent if they have the same function value and they belong to the same connected components of the level set. And again, mathematically, it's really taking the manifold itself and quotient out these equivalence relations. So let's give an example coming from, again, generated from TTK. If I have a height function on this, and if I select a particular function value, let's say this is function value A, what we have here is this is a level set of this function. This is another level set of the function. 2 points, that is x and y, that belongs to the same connected component of level set are considered equivalent because they have same function value and it belongs to the same connected component. So correspondingly, they are identified at a single point in the RIP graph. So in a sense that you can consider RIP graph to be the skeleton of the underlying function. So in this specific case, the RIP graph captures precisely the loopy structure of the underlying shape, but it also captures the location of the critical points as well. Okay, so that's called RIP graph. And finally, I want to introduce what's called Morse complex and Morse-Mel complex, is that when you have, in this example, it's a two-dimensional function. We use this to denote its gradient. For every single point in this function, there's what's called an integral line. An integral line is a maximal path whose tangent is aligned with the gradient of the function. So the idea is that we can sort of classify the points based on the gradient behavior. So this is what's called a Morse complex, is that if I have, say, a two-dimensional function, a stable manifold, which is each of those colored pieces, surrounding a critical point, in this case, a critical point is a local maximum, is a critical point itself and all the regular points whose integral line ends at this point. So another way of thinking about this stable manifold is local maximum and all the points whose gradient flow to those local maxima. So that's what's called, sometimes it's also called a descending manifold because the local maximum has a function value bigger than everybody else in this particular cell. And if I decompose the domain of my function based on this gradient behavior, this is called the Morse complex. So we have critical points, and the connection between the critical points, which are one cell, and then the two cell are the partition of the domain into those colored regions. So think about the sort of stable manifold as a one that is surrounding local maximum. Then the unstable manifold are the ones that is surrounding local minimum. So the stable manifold will decompose the domain into those two-dimensional cells, versus unstable manifold will also decompose the same domain into those color cells. And unstable manifold is that, if I have, for example, this is a two-dimensional cell of my unstable manifold, it includes the local minimum, and it includes all the points whose gradient move away from this local minimum, okay? So then finally, this is also called Morse complex of the inverse of F. And finally, if you take the intersection between the Morse complex of F and Morse complex of minus F, this is what's called a Morse-Mel complex. Essentially, each of those cells is an intersection between the Morse complex of F and Morse complex of minus F. One of the defining property of the cell in Morse-Mel complex is if you have points in the Morse-Mel complex, if I follow the gradient, it will flow to the same local maximum. And if you go through the inverse gradient, it's going to flow to the same local minimum. So another way to think about it is that you are basically classifying points based on their gradient behavior. 2 points are in the same cell if they have identical gradient behavior. All right, so there are a number of other topological descriptors that I did not cover. For example, things like joint contour net, things like Morse complex graph, and so on. There are several review papers in this space where you can go into more examples. Okay. So I just want to give one slide over potential applications, and we're going to see a lot more. Is that when you actually use those topological descriptors, you can perform a number of visualization tasks. For example, you can use them to study single scalar field in terms of symmetry detection, shape matching, and retrieval. You can use them to study time-varying scalar field in terms of feature tracking, event detection, structure change detection, and studying the space-time structure. Of course, today's tutorial, we're going to focus on ensembles, so you can use it to do clustering, classification, summarization, and interactive exploration involving ensemble data sets. So I actually gave some examples for all those different tasks, but for today's tutorial, you're going to see plenty of those. So I'm going to skip the rest, some of those nice examples to do shape matching, data segmentation, feature tracking. This is tracking of vortex cores, feature tracking of viscous fingers, and so on. But looking ahead, I think there's a lot of interesting research opportunities in terms of computational efficiency and stability of those topological structures, application-specific feature descriptors, and of course, integration of those techniques into interactive visualization pipelines. So I don't want to, that's the end of my talk.
I guess we can thank you for Okay, so hello everyone. My name is Charles and I work at Kitware. I will give an introduction to PowerView. I think most of you have already used it a bit, but I will still go into the fundamentals. This is a tutorial, so please do not hesitate to ask questions. Yes. Sorry. Please do not hesitate to interrupt me to ask questions. The goal here is to be interactive. So how this presentation will be structured. Sorry, I will just put a clock so I know where am I. This presentation will be first looking at the context of what is PowerView and the basics of the manipulation, and then we will see some news coming with PowerView 5.11. PowerView is an open source software which is meant to be used in the context of large data analysis. If you guys were in LDAV yesterday, I think you have seen PowerView more than once. It's really scalable, and it's maintained by Kitware and the community because it's open source. So the license is BSD3. All pull requests are welcome. And it's an end-user application, which means that if you want to use PowerView, you don't need to be a developer. You can just use the GUI. In fact, it's an application which is built around VTK, which is the library with all the mathematical stuff, the rendering stuff, the data model, and everything else, which still tries to be modulable, so you can just take the parts that interest you if you try to integrate VTK in your own software. And the goal of PowerView, as I already said, is to be really scalable, so you can use it from a small laptop, but it's also run on some largest supercomputer in the world. I haven't rated this here, but it's also cross-platform, so you can use it on Apple, on Linux, or on Windows without any problem. So let's put our hands into this software. I think you may have already seen the interface. So I will use here some examples that come from the TTK website. So we have a bit of topology inside. Here is a main
pair view windows with a small analysis on it. The first thing that we get is the render view with the datasets, which can be shown in different ways. So here we have a 3D representation, we have a chart, and we have a persistence diagram, as Bei just explained to you. We also have a panel above all of these, which will contains all useful actions that you may do with your dataset, like creating new filters, changing the representation, and I will explain some of them later. And on the left of your screen, you have the pipeline view, which shows you the current status of the filters and how they are related to each other, and places where all the panels, which will contain the properties of your filters, of your render views, and of the displays. We will see all of them into more details in a few slides. I just want to also introduce you a new kind of view for the pipeline, which is the node editor. It has been initiated by Jonas Lukasvik that will present later through a video, but which is also a huge TTK member. And this representation is really interesting when we are doing topological data analysis. As Yuga will see, the pipeline may be quite more complicated than just a linear suite of filters. So this graph representation may be a better way to grasp the semantic of the pipeline. I just have to say that it's still under development, and there are new features that will come into ParaView 5.11 and 5.12 for the node editor. Let's try to do some things together. So we will try to see how we can import data into ParaView. It's the usual stuff. As in any other processing software, you can just file open data or do it with Control O. So here is a ParaView window. I will just reset everything. And if I want to open a new dataset, I can just click on File, Open. Here I am in the folder which contains the TTK data. So there is a special repository next to the TTK one, which contains a lot of useful state file, specifically for reproducing everything that you have in the example that Julian told you about, and most of the things that you will see in this tutorial. And along with the state that we will see together, there are also the data files. So you can here choose any file that you want to open. I will try the Dragon, for example. At first, nothing happens because in ParaView, as we are meant to process really, really large data, you may want to configure what will happen before really processing the data. So every filters, every readers needs to be applied to really operate on the data. So here, for example, I could choose the scalars I would like to read if there was any on the data. The one I choose doesn't have, so I can just apply and the Dragon appear on my screen. Okay, so there is also some parameters that we can use to change the view, the properties of the view. So here on my ParaView, I have split the panel into several more. It's a bit, the semantic is better, I find, on this way. And for example, I can change parameters which are the parameters global to the scene, like if I want to see or not the triple axis of the scene or the center axis, on the display property, which has the one of the current data set or filters, which is represented on my screen. And this can allow me to change the representation. Like, for example, I can change to feature edges, and I have just the silent edges of my data model, which is not really interesting here, but still it's maybe more interesting into other data sets. The outline of other kind of representation. I can also change the color used to represent my data sets, and we will see more and more a way to interact with the data later. Representing the data is a thing, but most of the time when we explore the data sets, we also want to do some kind of processing. Here I'm not talking about huge simulation stuff, but just little manipulation on the data, like extracting a contour, clipping the data, or stuff like that. And this will be done using filters. So as we saw in the first slide, there is a filter menu, which allows you to choose which filters you want to apply on the data. They are classified into a lot of categories, and there is also the alphabetical menu, which gives you all the list of filters. And if you have TTK installed, you will also see all the TTK filters in their own category. I would recommend you, if you already know which filters you want to apply, to use the shortcut launcher. On Linux, on Windows, you have to press Control and space. On Mac, it will be the Command button and space. And then you can just type the name of the filters you want to apply. So for example, here we will add some Scalar data to the Dragon by applying an elevation. Here again, I need to go into the properties because nothing has happened yet. And I can change how I want my elevation to be applied. I want it to be along the Z-axis or the Y-axis and apply. And now I can see that my Dragon has a new scalar field that is available here, and which is the elevation along this axis. Do not hesitate to take the time to explore all the filters which are available into PowerView. And of course, we will see later, there is plugins like TTK that can add more and more filters into your application. This is what we already saw. Some other components that we have in the window that can be useful. We can do selection. So, for example, here on the top of the render view, there are tools for the selections, and I can select some points on an area that I grab with the mouse. We have introduced recently selection editors, which can allow you to create more and more selection and combine them together for more advanced manipulation. You can load this view using the view menu and selection editor. And here, for example, I have a first selection which is created in my dataset. And if I click on plus, this selection is recorded here. So now I can just come back here, select another part of my dataset, also click on plus, and I have both my selection available here, and I can even combine my selection to a new one. And there are more and more features that will be available into this editor, so you can precisely select the things which are interested in your datasets. This one is in 5.11. I will drop the selection here. Regarding the view, no, yes, this one is already seen. Regarding the view, you can manipulate the view to split the windows, which can be really convenient if you want to display both some charts, some spreadsheets, and some render view together using the menu here on the top right. So it's a usual menu, and when you split the window, you can choose what is the new rendering that you want to apply. For example, if I give here the spreadsheet menu, I will represent my elevation datasets with the spreadsheet where I have all the information regarding the points by default, but I can also have the information regarding the cells and everything else that can be displayed here, like if my dataset was a CSV file. Now let's look at some automation for PowerView. So I will show you how we can use the scripting to improve PowerView and how we can learn the scripting with PowerView, because PowerView patents, for example, that we may use is not, I mean, we need to learn the right methods to use. First thing for automation, we can save a state and load a state. It's really useful if you want to have like a checkpoint of your current status, and even if you have some troubles with the application later, you can come back to the current version directly. And this can also be useful if you want to share your works with some colleagues or other people's. This is the reason why on the TTK data repository you may find a lot of state files to reproduce the things that we have already done for you. There are two kinds of state files. The PowerView PVSM, which is an XML format specifically meant to be shared with the peoples, because when you load a PVSM file, you can change the input files which has been used to create the initial one. So even if you are in another computer with a different file hierarchy, you can still come back on your feet. And there is the Python state file, which is more meant to batch processing. The goal here is to record a state file and then to apply in a batch processing way the same mechanism in a lot of data sets on your own computer. Let's see together. So here I have this magnificent pipeline with like 2 filters, and I want to save this. So file and save state. I can choose between a Python or a PVSM file. Let's do the PVSM one for now. I will name it tuto. And now my file is saved. I will reset my session and reload this file to show you that I can get the same state. Tuto.pvsm. Here it asks me if I want to reuse the same datasets or not. I will reuse the same. And we come back exactly to the same place we were previously. We can also save an image of what we are currently doing. This is specifically useful when you are writing an article. So here, let's say we want this as an illustration for our article. I will just use the file, create save screenshots menu. I give it a name, like screen.png. There are some parameters here which can be interesting, like you have, for example, preset of a resolution. We may come back on them later. I can change the color palette, which will be used for the screenshots, and save this as a new image. And now, what I have to open my. Where did I save it? I will save it again. I'm not sure where I put it. Home screen in gray. Okay. And now I have my screen.png, which has been saved here. For the scripting parts, everything you do in the GUI of PowerView can be done using pvPythons, which is a way to manipulate the status of your analysis in Pythons as you would do with the GUI. So you can explore this using the Python shell. So this is also a view. So let's go into View and open the Python shell. Here, it gives me some prerequisites for the Pythons to be initialized correctly with the PowerView method. So this is a from PowerView simple import star. This is something that you should also write if you are trying to create Python files for PowerView to use. And now I can try to use some methods to interact with my pipeline. Like, for example, I will get the active source. So there is the method get active source for that. And it gives me a new object, which is the elevation that I am currently manipulating. And if I want, for example, to summon a new contour filters, I can use the contour and give it as input the elevation I just selected. And now you see that in my pipeline, I have a new contour filters that just popped. And you can do like that everything that you would do into the interface. If you want to learn how to do this, which methods correspond to which action, and so forth, the best way is to let PowerView tell you this. And for that, you can create a Python state and read what is into the Python state. But you can even start a trace and do your actions, and the trace will be filled with everything you are doing during the time when you are manipulating the interface. So I will show you tools, start trace, and I will also show the incremental trace. So everything that I will do since now will be traced directly. So let's summon the contour filters. Up. And now you see that PowerView show me a file which contains kind of the same things that I did previously, but it's a bit more verbose because it's also provides which scalars are used by default and some more information. The verbosity of this script file can be controlled in the initial windows. I was a bit quick on it. I will discard this and stop the trace. Yep. Finally, since PowerView 5.10 or 11, I'm not exactly sure, we have a Python script editor. So into the tools menu, you have a small editor which is given, which allows you to load the file, save the file, and which have more interactivity than the simple window that we had previously. This is specifically useful when you are using custom filters. I won't go into the detail here because it's not exactly the same kind of Python scripting that's what we see today. Now I will provide some cool stuff about ParaView 5.11. So if you have any questions regarding ParaView, the basics of ParaView, please ask it now before we go into the details of ParaView 5.11. Okay, so I will continue. I still available during the tutorial if you have any questions. The first thing I will introduce here is the 2D transfer function. So when we are into volumic datasets, and I insist it needs to be a volumic datasets, we can have a volume representation that will take into account kind of a bivariate data. By default, it will use a scalar value provided and the magnitude of the gradient of this scalar value, but we can also change it to be a real bivariate dataset. I will try to give you an example here using one of the VTI that we have in the ParaView state repository, the city bones. So here I will use a volume representation, and we can see it's a scan of a human foot. And if I want to use the 2D scalars function, I need to open the volume, the color map editor. So here, this menu can also can already help me change the color map, which is used to represent the data. Like, for example, I will try this one, which is already interesting. But now there is a new menu, which is Edit 2D Transfer Function. It needs a bit of pre-computation. At first, nothing is shown with this volume representation. But if I double-click here on this editor, I can now change the position of the new Gaussian function which has been created, and this will interpolate between the two coordinates which are given here. By default, I already told you the scalars and the gradient of the magnitude of the scalars. If I had another scalar value, I could go into the display menu and change the and change here the ordinate, the y-axis to have a real bivariate analysis. And for the Gaussian here, I can change the properties of this Gaussian using here the little square. So I can change, for example, the transparency and the colors. And maybe add another square. And with that, you can do some kind of interesting analysis in bivariate way. So this is the introduction of bivariate analysis in ParaView. Also, there is an expression manager for the people who use a calculator a lot, and you will see that in TTK it's often the case. Now it's possible to save an expression and to load it back in a future analysis, and there is also a window to get a summary of all the expression that you already saved. So let's open a new dataset. There is a special filters which is the calculator, and what I show you here is also available with the Python calculators, which just takes a Python expression instead of the expression I will write here. This filters basically allows you to use some mathematical operation between one or more scalars or vectors values which are on the data. So here I will create a new array named results, which will be simply the what is the name of my first? The first one is already named results, so I will change my name and I will call it new, and it will be the value of the old result scalar field plus 1. If I apply this, I have here my new scalar, and which is interesting, I can here save my expression. So it's write me that my expression is saved. And now if I remove my calculator, I'll come back on it. If I come back on my calculator, I open a new one, and I can save. I can see that I got my expression, which is here, already saved. There is an expression manager, which is a wall window which allows you to, manipulate all the expression that you have saved, because they are split between the simple expression for the calculators and the Python expression for any other kind of Python filters and stuff like that. I will quickly go with the resolution preset, because we already saw when we save a screenshot now, instead of always using the resolution of the screen, you can choose a different one with all the famous resolution already presets. There are a lot of other changes in ParaView 5.11, but we won't have the time to cover them today, so I just tell you to see the changelog, which is quite verbose, and there will be a blog announcement with everything in much more details. Any questions regarding ParaView?
Yes. When I see the 2D transfer functions, I notice that there's a background.
Yeah.
Like white to black. Does that have anything?
Yes, the background is kind of a histogram. It's a 2D histogram of the values, and I didn't show it here, but you can change the number of bins into the interface to have a finer resolution for this background, so you will have more control on the display. But be careful, if you have too much bins, it can cost you a lot in terms of computation. So that's the reason why, by default, it's a coarse one. Yes? I'm sorry, I don't really hear you. Can you speak a bit louder? When you save a state file, you do not save the result of the computation. You just save the applied filters with their properties, but you can also use the save data menu to save the result of your computation as is.
So the data is not included. All right. Well, in the interest of time, we're going to switch speakers to make sure we can have a coffee at 10:15. Thank you again, Charles. So now Christophe is going to give a quick overview of how to
that an application needs to run, such as libraries, dependencies, and so on, everything in a single file, basically. And why would you want to do this with TTK? Well, TTK as a piece of scientific software actually relies on a lot of libraries. It relies on ParaView in most use cases and so on. So there's a very large dependency graph. And if you just try to compile this on your computer, it's probably going to be at least an undertaking. So there might be conflicts with binaries you've already installed. You might need to recompile some of your libraries. And there might be all kinds of other platform-specific problems. For example, I'm on a Mac, and usually that makes for an interesting time getting things compiled. And so containers sort of address this problem nicely, because we can just put all of this into a container, all the dependencies, including ParaView and its libraries, and so on and so on. We don't need to have to do any installation. There is no recompile needed. We can just run this. And now you might say, well, how does this work? So the idea is that very similar to what a virtual machine usually does is there is a container. You install a runtime piece on your machine. It's called the Docker environment, and then you create a container. And inside that container, kind of like in a virtual machine, you can run ParaView and TTK, right? And so this is running on the host system. You can kind of think of this as a very thin virtual machine that doesn't actually bother emulating a whole computer, but only just the software and its dependencies. And this pays off sort of nicely. So a typical Docker image, for example, is 1.4 gigabytes in size for TTK and ParaView. If you did a VM that has all the operating system and so on installed in it too, and that's more like 10 gigabytes. So really taking a lot of time. And booting a VM, basically booting a computer, takes on the order of 20 seconds, at least on my machine, but getting the Docker image up and running is more like 1 second. So you get a lot of benefits in having sort of this thin virtualization layer. Yeah, and so getting a container going is kind of easy. You initialize a container from an image, kind of like you do for a virtual machine, and then the Docker engine is really this piece of software that you need to install on your machine that makes all of this work together. So you must install this to allow the execution of containers, but that's really the only thing you have to install. Actually, installation is super easy. I've put some alternatives here on the slide. It's available for all major operating systems, Linux, Windows, macOS, and it's typically fairly easy to install using a standard installer. So how can we actually make TTK work in Docker containers? ParaView, nicely enough, comes with a built-in mode that allows it to run in two places at the same time, right? So you can have the GUI running in one place, and you can actually have the backend that does all of the computation, the ParaView server, as it's called, in a different location, right? And typically this is used to run the GUI on one computer and maybe do the computations on a different computer, but we can leverage this to actually affect ParaView and TTK in Docker containers. We run the GUI outside the container on our native machine, and we run a Docker container that actually has the server inside, and then we connect the two of them, and then this works. So we can just download a stock ParaView from the ParaView website, any version we really like, and then we fire up a corresponding Docker container, and that then contains the ParaView server plus all of the TTK plugins and some other goodness. Right. And so how do you run this Docker container? Well, there's a convenience script that's actually included with the TTK sources that you can just run. It will try to auto-detect what ParaView you have installed, and then download and run a matching container. Or you go a little bit deeper and enter a Docker command that kind of looks very complicated, but I've tried to sort of parse apart for you here a little bit what these different options all do. You can do things like map directories from your host machine to the Docker container. You can tell it that you want to have the same user ID in the container as outside. You can tell it that it actually needs to open port 11.1 so that the container and the GUI can actually communicate, and so on and so on. So at the end of the day, this is sort of seems like a little bit of a magic invocation, but you can just use the convenience script or basically just copy and paste this, and it usually works. Let me show you how this actually can work in practice here. So let me hide the presentation. I have Docker Desktop here installed, version 4.6.0, but it should really work with any modern version. And then I can take this, let me make this a little bit bigger. I can take the magic command here, which conveniently I've already input, and just tell it that I want a Docker container TTK of version 5.11.0 because Charles did such a great job in advertising that 5.11 is awesome. Let's try to use that right away. We already built a Docker container for it, and we can just run this. And you can see if you've ever fired up PV Server, this is what PV Server says when it's listening for connections, and that was actually super fast and quick. Right? Intentionally, I did not download the container here because the internet here is a little bit wonky, but that's usually going to take about a minute or so to download that on a reasonable connection. And then we can just fire up the ParaView GUI of the same version, so also 5.11.0 release candidate 1. And then there's this little button up here that we can basically click to connect to another machine. We're not actually connecting to another machine, but rather to the container on our own machine. So let me actually delete this entry and recreate it from scratch so that you can see how this works. We can basically say like TTK in Docker. We want this to run on the local machine, so the host name is localhost and the port is 11.11.1. And we want to launch this manually, which we just did, and so I can just say connect, and voila, ParaView already connected to the container. Let me disconnect again for just a second. This is this button up here. Now you can see there are no TTK sources or filters or anything in here, but once I connect to the container, which I actually need to rerun again because it exits after, 1 second. All right, start the container again, and then connect again. All right, now we get a message here that says actually TTK is loaded on the remote plugins here, and now we have all the sources, for example, the TTK icosphere here, which wasn't available before. So all of this computation is running inside the Docker container. We don't actually need anything to do that. To do there, I can even maybe try and load a state file here, one that we have. I downloaded all of these beforehand. So let's take the Dragon, and then we need to tell it where to find the data files. This is all the normal ParaView mechanics that you would use anyways. And voila, now we have sort of here the TTK example running. All right, so much for the live demo. Back to the presentation. Just a couple of closing notes. Of course, we could also run this container on a different machine. For example, I could run this at home, or I might want to run it on some compute cluster that I have access to, and so on. Really, that doesn't really matter. The container can run anywhere, whether I connect to the container on localhost or I connect to the container on some other machine. That's not really a difference, right? So we can totally do that. There's one caveat. If we want to use this in a typical HPC setting, Docker requires super user privileges. So you need to be able to be root on your machine to actually use this. And this is a showstopper for HPC machines. But in these cases, you can use a different piece of software that's called Singularity that sort of containerizes HPC machines. And you can actually use the Docker images we provide directly with Singularity because they're compatible. And you can also use the mechanics we have here to build your own containers if you want your own portable environment. For example, you're developing some awesome new method within TTK, and you want to test this out on an HPC machine, or you want to ship your build to somebody else. Instead of telling them the build instructions, why not just give them a container? And we have all the scripts and so on in the in the TTK source tree, so you can just go under scripts and Docker, and then there's a Docker file, and you can just basically build an arbitrary combination of ParaView and TTK and whatever else you might want to add in there. We supply a bunch of pre-made containers. They are currently available on the Docker Hub. As usual, there are several combinations of versions, and then the developer and the stable branch of TTK. So just go there and look for a list. Typically, it's reasonably up-to-date versions of ParaView, and then coupled with TTK dev and stable. So you should basically be able to find what you need. And sort of closing this down, it's a fairly easy way to use TTK and ParaView together with Docker to avoid any form of manual installation that exceeds downloading a stock ParaView install. Why would you maybe want to prefer this over the TTK that's already being shipped with ParaView? Well, in the containers we provide, they're always up to date, basically from a very recent version of TTK. So there's no delay in getting sort of these latest goodies that appear in TTK. there, and plus all of the benefits that you get from containerization, such as portability of the code. All right, this was really a very fast tour of how this works. I didn't have time to go much into detail. If you want to know a little bit more about how we do this, how this works, and so on, I think we can do very few questions now, but I'm around for the whole day. I'll also be at Topo Invest this afternoon. Come and talk to me if you want to discuss in more detail. Different versions of TTK? Sure, you could have arbitrary versions of TTK in the container. The versions that need to match is the ParaView server version and the ParaView GUI version. So if you have a 510 GUI, you also need to have a 510 ParaView in the container. But you could have arbitrary versions in there. And actually, in my group, we use it exactly in this way. So some people developed algorithms and they built their own containers with their own custom ParaView versions, right? You can also vary the build parameters. You could say, like, I want extra debugging information or no parallelization. I don't know why you would want that, but maybe it's easier for debugging. Or so you are free to customize this any way you want. Sorry, I'm having a super hard time. Oh, is there a performance difference? I want to say no, at least not an observable one. There probably is one, but it didn't actually impact anything in our extents. The thing is really to understand about Docker is there's no emulation whatsoever involved, typically, right? So there's no fake hardware that needs to be emulated. It's just a process that's running on your machine, and the operating system is just isolating it from everybody else, right? That's sort of the key thing. So it thinks it has the machine to itself. It doesn't know anything about the libraries you already have on your machine, but it uses its own libraries, right? So there is an overhead basically for loading all of this stuff into memory, but that's super small.
Thank you.
All right.
If there's no more questions, we can thank Christoph again.